Alright, we come back here and we're going to get into the second part. Last time we were here, at problem 4.2-2. Now we're going to continue. So your rotation of our fixed axis. So now we know that the velocity, and we're going to write it in this way. Of course, be careful with the symbol that's used in this textbook, and that's for the unit vector, tangential. T for not time, but tangential is not very good to write this. But of course, some textbook they like to write this way. Other textbook write a very different way. So if you look at it, this is your velocity, okay, on a rotating body, and this velocity is the velocity in rotation about the fixed axis, which is, we usually call this regular velocity because it is on the path, on the circular path, which is resembling the regular linear, because linear has a path, curve, right? Curve motion. You have your curvilinear, I would say, because it is a motion along a curved path, and that velocity we are relating to the rotation, okay? Again, your axis is poking out of the page the way that this book is doing. And then, of course, when you draw like this, you have your angular velocity here, going in that direction. So your regular tangential velocity is going that way, and then you have your angular velocity here. That's a regular velocity, angular velocity. This is the equation that is linking the regular velocity on the circular path with the angular velocity happening around that fixed, okay, point in the rotation. All right. So now, and that is again your distance from here to here. And then of course, that is referring to, what if we're just looking at a unit vector? So your unit vector is happening here on this tangent path. So therefore, we call this a tangential unit vector. All right, and that's how we can be able to get the regular velocity out of angular velocity if that's given to you, and we know the distance of this, we know the angle of that, and we're going to put the constant, which is your ET, for showing you actually the direction. The direction is always that way, okay? Alright, so here you know that your velocity is always tangent to the circular path, which is this guy, And again, that velocity is a regular velocity, okay? Your angular velocity is right here. And it is along that ET line right there, which is tangential. And that's just showing you the direction. Remember that we define the direction with a little k hat. Now we're going to use a symbol ET, okay? I usually just go with this axis, so if I go with the z-axis, then I go k, x-axis, because you can flip any three axes in any way you want, by the way. Not always this is x and that's why you can flip it around, so you have I, j. So some of the very, very difficult professor will flip that axis and you have issue, because you always like make like that's the z and that's the y or something like that. Some people flip the y and z, okay, axis like that. That depends on how you look at it, okay? You can still rotate your axis anyway, but it is the same thing. Just know that which axis that you're using. So depending on what axis you use, your direction can be I, J, or K. But right now they want to get rid of that because I think this author confused. So therefore they just go, I'm just going to go with the tangential direction, and they just wrote it ET. So tangential direction, which is your tangential unit vector. And that's how I am going to define the direction in this book. So that's what the author just did that. You also have another direction, E and then theta. That's a radial direction. Again, you can, like I said in the beginning, you can flip that to axis. And that is, I think, the most confusion student usually got it. Like, one book is writing tangent on the thumb and the finger is the rotation motion, and the other one is a flip around. It is because of the way that you take this axis. your three different coordinate axes. And never ever forget, the farther the point on the rigid body, the farther the point from the fixed axis, velocity is faster, yeah, greater. I'll give you another example. Let's say you have like a old school CD, yeah, music CD, and you rotate it. So the spinning CD, the point on the edge, okay, is going to move faster than the point at the center. Okay. Of course, we're going to get into another derivation, and this time we're going to derive acceleration, yeah, of any point on a rigid body, and going pure rotation. We're still on the rigid body, and we're on the pure rotation of that rigid body, and we're looking at any point on that rigid body, and we are going to get acceleration, yeah, and we will put it into mathematical formula. So we have radial distance is r, which is from here to here. Your angular speed, which is this guy, okay, is going to be omega, omega. And then your angular acceleration, the one that we're trying to find, is your alpha, yeah. We're going to put that into there. That's a regular acceleration on this circular path, which is, we call it arc, yeah, because the arc is a path, which is a curved path, yeah, it's just a line here, but it is curved. So therefore, we can be able to apply the regular acceleration there, and then we're going to link it, to the rotation, yeah. So now we have v here. That's a regular velocity, final regular, yeah, velocity. And then here we go into a little bit of a new, okay, row here, and I will tell you what that is, okay. And now don't forget, all right, where we are for the v dot, yeah, and that's v squared, and this is your r dot, and then this is a theta dot. So you're going forward, yeah, position, velocity, and acceleration coming backwards, yeah. Every time you do differentiation, there is a dot, yeah. So that's what it is showing here, for you to be able to, then that's your direction, which is tangential, and this is your normal, which is perpendicular, and of course this is radial, which is along that, okay, theta. Yeah, we have three different direction that is accompanied each of the velocity that this rod has experienced, okay. The acceleration depends on the velocity changes, so therefore we have a 2 here, and then your velocity depends on the position changes, yeah, therefore you have this theta. See, it's just showing you little dot mean I'm changing, yeah, a little dot here mean velocity changing, therefore you're getting acceleration because your velocity change, yeah, and that velocity is on the tangent line, meaning it is defining my velocity is direction tangent to that path here, okay. And of course you have another velocity, yeah, and that velocity direction is normal, yeah, meaning like I am normal, centripetal acceleration, yeah. You have two different acceleration. One is a tangential acceleration that the object experience right here when the motion is on this path, and the other one is there's another motion that is happening on the same rod, which is your normal acceleration, your or centripetal acceleration. And that happened because of the change in the direction of that motion, yeah. And again, we're breaking every part of the motion. And then you also have a radial, which is this guy, and showing you with this angular, yeah, position change, yeah. So dot mean change, angular position change, and that also angular position is also a vector, and that direction is going with this, all right, radial direction. And of course this distance from here to here of that rod also change because it goes, yeah, from here to here, and that one doesn't really change that because the shape of the rod doesn't change. However, it does have a change in position as the rod, the whole rod going, and that is again ER, okay, which is going to the radial direction as well. And you know that this tangential acceleration, right, this guy, yeah, is always caused by the angular acceleration, okay. So angular acceleration will have effect on the acceleration that happened on that path. Yeah, so the rod is experiencing two distinct acceleration. One is a angular and the other one is a tangential. Yeah, two different here region and this path, only that path. Okay, and don't forget the points. Yeah, where they are. And your centripetal is this guy. Yeah, your centripetal acceleration is an. Depends on what the variables are going to be, what values are going to be. So if you get like the 0 right here, you're going to left with the only centripetal acceleration because of the change in this velocity and not that one. Yeah. And so in that case, you are definitely left with the centripetal acceleration, and that is caused by the constant change in direction of that motion. Okay, that's a little bit difficult for you to be able to understand where the acceleration is. It's just that, like I said many times, you have a body and it is made of many different points on that body. Yeah, and of course, and they have a different velocity, so therefore they have different acceleration. Okay, so if you want to simplify like that, you can be able to understand that way. And your velocity, yeah, this regular velocity on here is related to your angular velocity with that much of distance away. Okay, and then your acceleration, yeah, this is your acceleration, regular acceleration on that path is related to the angular acceleration, okay, with that distance away. Okay, very easy to read. It just you may have a difficulty trying to relate the symbols, right, with the meaning. Yeah, so make sure you practice that. And E's are just showing you the direction where they are. That's angle. R is this direction, the whole thing. N is angular, yeah, which is perpendicular to that. We call it normal. And T is a tangential along that line. Yeah, be careful. Yeah, there are many different regions. And why do we have many different accelerations? Because your velocity, they're not the same along that body. Yeah, so there are many points on that body taking position at different distances from the fixed center. Yeah, that's why it experiences different acceleration, and also the direction of the acceleration depends on where the point is and how you're looking at it. Okay, angular, normal, tangential. Okay, normal is a centripetal, which is pointing this way. Tangential is on that path. Yeah, tangent to that path. Angular is this guy. Okay, which is radial. We call it radial. And of course, we also have another, which is this guy here. Yeah, loosely call it radial as well, but it's okay. Another way that we define E theta, even though we loosely call it radial, but that you can call it angular. Yeah, angular. And R for radial, N for normal or centripetal, and T for tangential. All right, be careful that three factor. They're all different directions, by the way, and happening when the body rotates. Okay, and taking a circular path. Then of course we get into more into the derivation of the acceleration, and starting from there, and then we come to here. Yeah, so acceleration is r, and the angular acceleration, regular velocity is r, angular velocity. Yeah, very simple. And of course we are going to put all of it, plug it in, yeah, into this, right, r theta, so we're gonna get this. Yeah, we are just plugging in this v into that. So r offer et r omega square en, and then r offer e theta minus r omega square er. Okay, is going to be, this is just a change in the direction, which is your radial, okay, direction. radial direction is only 2. You always have a 2 direction for any unit vector. So anyway, that is showing you the direction. This is magnitude, direction, magnitude, direction, magnitude, and direction, magnitude. The script is telling you where that direction is, where this E is just a unit vector. That vector is tangent. That vector is centripetal normal. That vector is on that angle, angular. And this vector is the whole rod, which is radial. Then we will get into the acceleration. Regular, again, A for regular acceleration, and then we're going to link it, and this is our derivation from the previous. And of course now we get a distinct relationship between the regular acceleration on that circular part, and the other one is on angular acceleration, which is happening here. At the rotation, okay, which is around here. Your offer is, your regular acceleration is pretty much on that part, pointing this way or that way, depends on where you're looking at your axis. Then we come into example 4.2-4, and here we're thinking about this wind turbine, and we're thinking about what is the velocity of the center. So your center is right here, you see that, and your motion is going that, circle like this, and you want to know the velocity of that center. That's going to be 0, because we always say, your axis is not here, your axis is going into the page, by the way, going into the page. So therefore right here your velocity is 0, because your velocity is the strongest out there, and then go weaker and weaker and disappear at the center. So therefore the answer is 0. So here is the answer on the next slide. And then of course we go the second problem. Here I'm just gonna go ahead and explain that to you. So we're paying attention to the angular velocity, which is your little omega. And of course every time we think about the angular velocity, since you have many different points having many different velocities, we're gonna pick a point and we are gonna concentrate at that point A. So right here we know that the velocity at B is greater than the velocity at A, by the way, because the point A is nearer to that center. So anyways, the point A is a midway between the center O here and the tip of the blade is B. So the tip of the blade is Colette, sorry. So here is talking about this point B and then point A. Sorry, somebody came in and I went out. I'm back now. So anyway, so when you think about velocity, we have a 2 different velocity going on. So we have velocity on the path, the circular path, and I already told you there are many different paths, and then the velocity at the angle. So the angle they have the same, and for the velocity on different circular path, they have different velocity, and the nearer the point is to the center point or the fixed point, the smaller the velocity is. Okay, so right now you're asked for angular velocity, not regular velocity. So therefore we have to concentrate on the point, and all these points has the same angle, so therefore angle theta, so therefore you're gonna have the same angular velocity. Okay, so if you think about the regular velocity on the curve path, you have a one circle here and you have a bigger circle right there, circular path. This guy is the velocity tangent to the bigger circle, and that is greater than the velocity tangent to the smaller circle, point A. So this example is the first example to show you, the distinction between the angular velocity sharing the same angle and the regular velocity on different circular path. Depends on where your point is. Okay, so this example 4.2-4 is very, very important for you to understand the regular velocity and angular velocity. Okay, because you have a, even though we call it pure rotation, it comes with the micro, micro motion that is happening on that is happening relative to that pure rotation, which you cannot ignore. Yeah, meaning like your object is subjected to two different velocity. Okay, because and that just tell us how the points are they are experiencing different, different amount of velocity at different places in the same body. All right, so very, very important, seriously important key point that you are learning, okay, from this slide. All right, and then of course we go in now regular velocity. See, the velocity of point A, which is this guy, is blank, that of point B. Okay, so it's got to be half. Yeah. Okay. Then the next one, again, don't confuse with the angular velocity. You are talking about the velocity on that path only at that point. Okay. All right. Then we have another example, and this one is 4.25. In your interactive textbook, your cat is this guy, and that sits without slipping on the edge of a spinning disc, and the disc is turning in the direction shown and slowing down. Yeah, so this is your disc is going in a pure rotation, turning. Yeah, of course, actually going that way, so clockwise direction, and that cat is sits right there at that spot on that disc, and it isn't slipping out, of that disc. So it's just sitting on the edge of a spinning disc. So now we have everything, and pay attention to how the author is seen. So I was right. See, she took the Z, yeah, straight up. I usually take the Z that way. I usually take my Y up, by the way. So anyway, so they're taking the Z up just like in the cat, model. And let's go down here. Yeah, so you have many different directions, but only for three axes, of course, your x and y and z axis. Each axis have a two direction, going that way and going opposite to that way. Yeah, so that's what you're seeing right here. And of course we are on the z axis right here. Yeah, so she is looking at this fixed axis is on the z-axis, so therefore your radial component will go that way. Yeah, so which is x-axis. So now we identify which axis that this author is using to. That's why she gave you this axis icon. Diagram here. Otherwise, you're gonna have an issue if the author doesn't define this. So at the instant, at this moment, point of time, what is the direction of the radial components? The radial is not the fixed axis. Okay, radial is something that is crossing the fixed axis like this. Yeah, so therefore we're on the x-axis, so you can delete this immediately. Yeah, now you have this and that. So we have to take a look at how this thing, the motion is going that way. Okay, so you will draw your x-axis like that. Yes, so you have a positive direction and negative direction, and your motion is going, by the way, this way. Okay, so your radial is this angle right there. Your position is changing. See like how it is changing. So we would say like in your direction is showing your angular velocity direction going that way. So we are going to make the x-axis. This is, sorry, I should write it x-axis on this side like this, so this is easier for you to see it. All right, x-axis is like this. Yeah, so therefore the positive x direction is there and the negative x direction is there. Your angular velocity is going that way, so therefore we're going negative x direction. Yeah. Anyway, so yeah, so this is your the answer. Okay, if you don't want to draw it here, you can also draw this way. Yes, and your z is right there. She said it, so your x is here. Yeah, you can draw like that way, and going this direction. Yeah, so therefore that is a negative x direction. It's a little bit difficult for you to be able to see it, but try to understand radial, yeah, word. Radial meaning like radial distance, yeah, from the center. And don't forget the point is your cat, yeah, because it is said so in your problem, okay, here, yeah. So if you're wondering, well, where's my point, so your point is cat here, yeah. So radial mean is going towards that z axis right there. She said z right there. Okay, I hope you get it. It's a little bit hard, but yeah, you should try to understand how it works. Okay, it will confuse you. The radial, the centripetal, the tangent, and the angular. And then we come to the next question, and here this time we are doing tangent. Yeah, radial is that way on your x-axis, and the tangent is this guy. Yeah, and it's here on the circular part. So you're on the y. See like how we draw it is to understand your z, your x, and then your y. So your y is going to the positive. If you put this positive direction, it's going to go to the positive direction. Yeah, see how easy that is. So you draw tangent of that cat, because we are defining the point on that disk. Yeah, the point, the cat is not a part of the disk, but that cat is on that point, okay, of that disk, at that point on that disk. And because of this definition here for your 3-axis, we know that that's your y-axis, because your tangent component is going that direction. Yeah, and we're going to the positive direction. All right, the next one is we coming into angular. Yes, angular is your theta. Yes, see like how each one is trying to teach you what they are. And the last one is your angular. Angular means this angle here, yeah? So they already show you the motion direction is going that way, and your angular is on this z-axis, yeah, happening. So you're going to use your right hand rule, yes? So you will put your fingers pointing to that direction, yeah? So your finger thumb is going to go, because your little fingers, yeah, is going to go to the direction of your angular velocity, yeah. So these are your fingers, and so it will point, okay. It's hard for me to draw it, but what I want to say is like your finger is like this, and all of your yeah, your thumb is down like this, and your finger is showing the direction of your angular velocity. Okay, so therefore it is going down. Okay, so that is a negative z direction, because she said it. So yeah, this is z direction. So therefore this guy. Yeah. Okay. So make sure you practice the 4.2-5 conceptual example to understand very clearly how we use a 3 different axes. Yes, this angular, tangent vector, and then this is your centripetal. Okay, I would say centripetal is a normal, because here in this book they use a little r, yeah, version. So r for x and t for y, and then theta for z for this book, because of how she defined it. Yeah, if you change the book, you will pay attention, like I try to look for it. You know, because sometimes we switch. Y is Z, and then Z is that. So anyway, so this is your whatever video for this turbine, and we can take a look at it. So this is a video. Let me put it by all the way from the beginning. You can watch it at home, okay? It's just showing you how fast that is. Oh my gosh. See like how this wind system failed and then it crashed. That's bad, yeah. The next section we're getting into gears and belts for mechanics. They're very important. This is just trying to show you there's a TV show Deconstructor Razor. And of course we usually represent the gear, a diagram like this, a very simple one. So you can be able to see it visually. Yeah? So what we're doing with the gears is we are changing the rotational speed. Okay, so these are all rotating. Yeah, we call them gears. It's because see like how they are connected to each other, and then look at the belt. Yeah, connected to each other through these pulley system right there. Yeah, you have one pulley and the second one here, the pump here. AC, so that's parts inside of your car. Yeah, mechanical parts. So sometimes it is important and it's necessary, to transfer the rotational motion and change that rotational speed. Yeah, when you take a look at it, here is a CAD model showing you, how this rotational speed has been changed. And we use, of course, gear to do this, changing the rotational speed by using the gear system. So if you think about two gear system here, you have to think about the rotation at this bigger gear and the rotation at this smaller gear. They're gonna coordinate each other, and the two motions, that happen here and happen there, they're gonna coordinate, with at that point of contact right there, So it's very important for us to understand what is the velocity of that point of contact. See this where they touch, this big gear and small gear come into contact, that way. See now how the gear teeth they fit each other. So we call that the contacting point, and of course the corresponding angular velocity, and the distance of the point from this fixed point, and they are there, but they're different because of the size of the gear are different. So when you look at it, here is your angular velocity of the smaller gear, and then you have the distance of the point of that gear to the fixed point of that smaller gear. And we are gonna take a look at very carefully of this, the point of contact, and analyze the velocity at that point. Velocity at the contact point. And of course, when we come to the mathematics, we're gonna write the same thing: regular velocity. Some people call this tangential velocity. It's okay. Is equal to your r, the distance, and then the angular velocity, which is happening around that. In this book, z-axis. So your v1 is the point of contact, which is this guy that we're analyzing. It's equal to v2, the point of contact. We call this v1, and we call this v2. V1 for the larger gear and V2 for the smaller gear. You can also flip it, it's the same thing. They're just a symbol, represent two different. So you understand that there are two different velocity happening at this tangential point, but at this contact point, they're the same. Okay, and that is what this second formula is telling you about. So all the mathematics formula is explaining what's going on right there. First, we know that there's a gear, two gears, and they are moving with a tangential velocity corresponding to angular velocity, and with that factor, which is the distance away from them. And then we are going to put that, because the V at that point of contact is the same, so we can equate R1 W1 equal to R2 W2. How that's so easy. So therefore we can be able to find, by using the algebraic mathematical operation, we can be able to find any of the variable without the magnitude. So if you have the magnitude of this, and you don't know this and that, we can be able to find that out. So here we're trying to find the angular velocity of the second gear, and we can get it if we knew the angular velocity of the first gear, and of course we know the radius of the gear because that's your mechanical part, so you definitely have a measurement or dimension of that, accurate dimension of that, so you just plug that in, so we can be able to figure out what is the angular velocity of the smaller gear, vice versa. You can also find the angular velocity of this if you knew the angular velocity of that. Alright, so mathematical formulas are all about relationship. We are relating the variables on one side of the equation to the variables on the other side of the equation. So this relationship is going to work for the gear, pulleys, your belts, contacting wheels, everything that is coming into contact. We can be able to use this to find these variables in that equation. Your extra gear relationship, which is we put instead of r this distance here, we can also put the n1 and n2. Okay, your n1 and n2 is nothing but just representing this extra gear, which is extra gear relationship meaning the belt on it. In this case is the belt on it. Alright, then we will get into fixed axis rotation. In fixed axis rotation, you can skip it because of this anti-coordinate system. We're not doing it. So I'm just going to go ahead and tell you what slide to skip. Skip this, everything that is off anti, because we didn't cover that anti in the chapter 3. So therefore, you don't have to do the cross product review. Actually, cross product we can actually do this, but I wouldn't ask you to do any of this. This is belong to the NT, so therefore we are going to skip that for you and go straight. Okay, I'll just go all the way down, and we're going to go straight to the general planar motion. So please skip from NT and come to the chapter 4 general planar motion, because we don't cover NT on the chapter 3, so you don't have to do that at level 2. Alright, we have a relative velocity and acceleration. That just showing you the animation, to make this rigid body kinematics visible. We can go up to that website and take a look at it. So it is with this animation, so we can see what kind of motion is this, and you have a rigid body, showing you the circular path here, and your fixed point is right there. So when you look at a pure rotation, it just did. When you click on the next, you see this little picture like that on the animation slide, and this is your fixed point of that rigid body. So don't forget, you have every point on that body is going to move in a circular path. So you have circular path, many different circular path like that, not only here. Now let's take a look at what kind of motion is this. See like how it is going this way, and you understand that it doesn't really change, so therefore it is a translation. Because there's no rotation, that bar remains parallel throughout the motion. So again, don't forget the parallel mean like that. This line and that line. The way that I draw is, so anyway, so this is parallel to each other. We use two little lines to identify the parallelism. And then the next animation is showing you what kind of motion is this. It didn't rotate, it just translated, but it translated on a curve. So therefore that is a general planar motion, because at first it's translated, and then it's rotated on a very, very shallow curve. So that will be your translation and rotation happen at the same time, slightly. And let's take a look at it again. And then rotate. See that? First translate and then second rotate. So first the bar translated and then rotate. So you have your start point and end point. So your start point here and your end point position, see, pay attention, perpendicular, and then it is at an angle, the endpoint is. Yeah. So your general GPM, general planar motion, you can break it up into first translation, and then the other one is your rotation. Okay, so that's for this animation. Of course, this is a handout, so it's not active here. You will have to go back to your interactive textbook to click on the animation. Yeah? Now we come back to the general planar motion, and it is a combination of your rotation and translation. You have translation happen and then rotation happen later in the previous example. Yeah, and here just showing you general planar motion in mathematical formula. You have translation plus rotation. This is just showing you is a combination of the two different motions. So the very first one is you go from here to here, that's translated. Yeah, so translational point, and the second one is it rotate. Yeah, so the rotation is going from here to here, and it is happening with the fixed point A. Yeah, this one is just a translation on a path. Yeah, curve path. They're all different, by the way. Curvilinear, rectilinear, and your general planar. Then we get into example 4.3-2. Yeah, and we'll have to derive the equation for the velocity of point A. So you're going to start with a very pure rotation. So here is a regular velocity happening at the tangent position. And then you have an angular velocity, which is this guy. And then you have your distance, which is your r. And relative motion is when we take a look at each one of the velocity, at different points. So you have an A, then you have a B, okay, you have an A/B, we will go into each one of them because we have to derive the equation for velocity of point A, which is this point. So let's see how we do that. And if you pay attention to this, you know that this is your rigid body, and this is your point A far away from the fixed point, which is this guy, because your rotation is going on that way. It's showing you your acceleration, angular acceleration, and angular velocity here. Your translation, your path, all right, the curvilinear path, there's only one here because we're concentrating on point A. So we draw the circular part, only one here. The tangent is your regular velocity. Along with the regular velocity changes on that path, you have a regular acceleration, okay, pointing that way. And relative motion is point to point. So we will concentrate in the velocity at this point, regular velocity, by the way. And then, of course, another point is here. You also have a zero velocity here, so velocity at that point. And then look at this. Look at this. So that's a tangent to that point. And it also comes with its own acceleration at that point B. So don't forget these things. And we will take a look at that relative motion. So we start writing the pure rotation. The other one is, so what is the velocity of point A? Point B fixed. Point A is rotating about the fixed point B. And we want to know the velocity at that point. And you will have this. You can calculate from here to here, and then your velocity, angular velocity. Angular velocity multiplied by the distance of A from the origin is going to the center or fixed point. We just say origin or O, and that is going to give you the velocity at that point. So if you know the velocity at point B, you can be able to find the absolute velocity and acceleration at that point A. Okay, so how do we do that? We use a relative motion because they are all relative to each other. So your velocity at point A is equal to velocity at point B, and then you're going to add the velocity, A/B. This is just looking kind of like I wouldn't say a combination, it's just looking at both points at the same time. Yeah, and then of course VA is your angular velocity times the distance again. Yeah, between A and B. Why? Because now the B is kind of like, yeah, even though our point, yeah, the distance point is we put it outside our rod, yeah, which is your rigid body, is kind of like that much of the distance away from there. But of course we can be able to measure from here to here and then from here to here, because our inertial coordinate frame is off of the body. Okay, so we don't confuse between the inertial coordinate frame axis and the axis that we put temporarily at a point on the body. Yeah, people get this is a axis for the inertial frame. Okay, meaning like that doesn't move, but that this one did move. Yeah, away from here, your reference frame. This happened quite a lot in CAD modeling. Yeah, so you have your world coordinate at a point, and then you draw somewhere in the space. So your final body is so far away from the origin like that. Yeah, you can also put this frame on the body. But anyways, in this case, your frame is away from the motion, okay, of that rigid body. Then we will continue. Yeah, we know the velocity of point B, and we're going to get into the absolute velocity and acceleration of A, starting from this relative motion, and we will put, okay, instead of B and VA, yes, we can be able to put that into, plug it into this velocity, okay? So we use, which is your omega, yeah, that's your angular velocity times your r between these 2 points A and B. And of course, when you take a look at it, if you want the velocity at point A, yeah, you're going to use the velocity at point B, and then you're going to use the angular velocity, and then you're going to use the distance between that 2 points. That's what it's saying here. Yeah? Okay? Very easy, yes? If you want to get the velocity at point A, use the velocity at point B at the angular velocity of that body times the distance between that 2 points. Okay, that is what this mathematics is talking about. Alright, so then we are going to derive the equation for the acceleration at that point A again. Yeah, so we're going to start with a pure rotation. We know that we can link the regular acceleration to angular acceleration by using this equation. Yeah, your distance between A and O, see, okay, and then minus your omega, which is your angular velocity square, times your distance between A and O, which is your inertial coordinate frame, okay, meaning like this is fixed right here. Anyway, so the relative motion, we have a relative acceleration, which is acceleration at point A. You can get it from acceleration point B plus acceleration between that two. Yeah. So let's see. We use the same thing here. Your acceleration, regular acceleration on that part, which is this guy, is equal to your angular acceleration times your distance between A and O minus, yeah, and angular velocity square, and then your distance between A and O. Okay, so that's what we use to get the acceleration at the point A. Now we're going to put everything all together, and you get the acceleration at point A is equal to, we're going to use the angular acceleration and the distance between r, which is r between A and O, okay, and then minus omega, which is angular velocity, the whole square, times the same distance, yeah, from here to here. Another way that we can write is angular velocity, okay, regular velocity, regular acceleration at A is equal to angular acceleration times the distance between A and B minus angular velocity square times the distance between A and B. Okay, so you can get it in two ways. One is using the distance between O and A, meaning like using the distance of the point A from the origin, or you can use the distance between, all right, the 2 points on that rigid body. Okay, I hope you get it, so please study that. So we know the velocity at point B, yeah, we can be able to find the absolute velocity and acceleration at A, yeah. So by using this relative motion, you can get the acceleration at A by using the acceleration at B, and then acceleration between the 2 points. So acceleration at A, regular acceleration, is equal to, we'll use this angular acceleration times, yeah, the distance between A and B, minus velocity, the angular velocity square, yeah, times the distance between A and B. Yeah, so this is what it is showing you that. And put them all together, so you're going to get angular acceleration at A is equal to angular acceleration at B plus regular acceleration at B plus angular acceleration times the distance between the 2 points minus angular velocity squared times the distance between the 2 points. Okay, so make sure you look at the physical thing and what's going on, and then apply that in there. You have a regular acceleration, regular velocity. You have an angular acceleration and angular velocity, and then you have a distance of a point on the body to the origin, distance of a point on the body to another point on the body. Okay, that's what we're playing with. Alright, then we slowly get into the relative velocity and acceleration to define your planar, general planar motion. So the very first one is from again, your translation. The second one is your rotation. Yeah, so we can clearly see velocity, regular velocity at B, and you have a rotational velocity with the distance, and that rotational velocity is happening between the 2 points on the rigid body. Yeah, so this is how we can be able to understand that. When you look at the acceleration equation, you know that that's a translation because that's a regular acceleration, and you know that this bar is rotation because we're dealing with the rotational, which is angular acceleration and angular velocity here. Again, the same thing between 2 points on the rigid body. Okay, don't forget there's a point of origin, which you can use the other equation as well if this equation is given to you. Of course, I am not going to ask you the calculation. You only need to know like what variables that we use to get which variables. Yeah. Then of course we get into the little problem here. It's just asking you in your interactive book, and here you're given a rod, which is this little rod right there, AB. That's gonna slide inside of that ring C, and if that rod never loses contact with the ring, what direction is the velocity of end B, which is we're concentrating at this point B on that rod, relative to the end A, okay, of this one at the instant shown, which is instant mean at this moment. And of course we have this direction given to you, and you have a lot of look at this direction that you can choose from A all the way to A. So in order for us to come up with the direction, we gotta understand what's going on with these axes, and this book is using Z as top. So here you can see that this is going, look at this direction. There's only one direction that is given you. So when you look at it, your end A is moving that way, which is your counterclockwise. So your clockwise is this way. So going this way is a counterclockwise direction. Alright, so that's the first thing that we recognize. And then of course your rod is rotating, your A and B, got a velocity, it's got to have a velocity, but that velocity is relative to A. That follows this. You have an instantaneous center of rotation is happening, on that rod, because they don't go out of contact with this ring. okay, and the rotation is happening that way, okay. So we gotta come up with the direction, but it has already identified, yeah, the counterclockwise direction, yeah, for you by showing you this little thing right there, okay. So if that rod is moving counterclockwise, meaning this guy is moving to that way, okay. So your B gotta move in order to balance that, yeah, um, because the rod is positioned vertically down like that, yeah. So if the rod is moving, A point is moving that way, yes, and the rod doesn't come out of contact with this ring, yes, it's got to move down, yeah, because if it's moved to that way, uh, the entire rod will get out of that ring. Yes, if the rod point B is moving this way, yes, it is also going to, yeah, stay without any kind of motion because this and that will cancel each other, yeah. Um, but it's still in the motion and it's still moving, you know, inside of the ring. It just that doesn't come off of that contact. So in order to balance this counterclockwise going that direction, you know, it gotta go this rod, not the B point, but the rod gotta go downwards. Yeah. So when you think about just the point, yeah, just the point, in order to balance that, since this point, yeah, um, is showing going this direction, yeah, your B gotta go at that point, go this way, not the entire rod. The entire rod is gonna go downwards because of that motion. So if we concentrate the word, yeah, it said if the rod never loses contact with a point, we've got to make sure that this rotation happening to the entire rod AB, all right, is concentrating only at that point A, yeah. So therefore, in order to balance the point A, your point B on the other side, yeah, got to go this direction, okay, because the entire rod is going counterclockwise. So in order for the entire rod to go counterclockwise without coming off of that ring, you must have a two, yeah, two action and reaction, yes, forces happening at the extreme point, which is A and B. So the A gotta go that way. So therefore, the velocity at the end of B gotta go this way. Okay, the entire rod will go downwards. All right, so let's see what is. Yeah, yes, correct. Yeah. So anyway, so because the most important word is the rod never loses contact with the ring. Okay, and that told you that the velocity is a change in position. Yeah, so this two contact point got to be in opposite direction to cancel that. Yeah, motion. So make sure that you actually read the question. Yeah, so what direction is the velocity of end B relative to end A at the instant shown? Again, the word end meaning extreme point. Yeah, we're not interested only in that 2 point, not the entire rod. If there's no end and it's ask you the direction of the rod, you're gonna go say like go down. Yeah. All right. Then we will come into the mechanism. And so the most common type of rigid body kinematics analysis mechanisms. Yeah. So that's the rigid body kinematics, and we are analyzing, the aspects of motion. So mechanisms are, they they are designed to change your direction, your speed, and then your type of motion. Yeah. So right now, of course, two sentences is going to get you. So if you think about the mechanism, uh, this way of writing doesn't really explain anything to you. Yeah, because first of all, you don't know what kinematic analysis is, even though it's all the aspects of motion. It's just mechanism is just a system. Yeah. So you in a system you have system is always composed of many different parts. Yeah. So since we're in the rigid body, your system is composed of many different connected rigid bodies. Okay. So a system of rigid bodies. And since you have rigid bodies and we're studying the motion, they're gonna have a different motion. Yeah. And they will transmit a different motion, and that type of mechanism we're talking about. Yeah. So not the single kinematic, not the kinematics of a single motion, but mechanism meaning is always a system. Yeah. Mechanic meaning like there are many different bodies inside of that system, and we will analyze that. Yeah. So mechanisms are a very basic or fundamental part of your rigid body kinematics analysis. Yeah. Kinematic is just we're analyzing the motion. Yeah. And of course mechanisms are they're used, of course, these systems to see the change. Yeah. So when we think about the change, we look at the direction, we look at the speed, we look at the type of the motion. Yeah, these bodies are experiencing. So yeah, you can convert the rotation to translation. Yeah. Your speed, we can look at the speed of the gears in the system, or if it's a direction, we can look at the car, right, steering system, how you use it every day to turn, right, here and there, everywhere, and go, keep going to the forward. So anyways, your steering is a object that is indicating how your car is rotating, okay, and translating, by the way, translating and rotating. So your general plane of motion is at the point of your hand, on the steering wheel. All right. All right, this we gotta go back to our textbook. Yeah. So here it is showing you a piston. Changes linear motion to rotary motion. So here there's your rotary and there is a piston, and let's take a look at how that is going. So you can see this piston. See, that is your linear motion. Where is my pen? So this is your linear motion, and another motion is this one. Rotary motion. So that's what this slide is showing. Yeah. So you have your rotary, and then you have your linear, piston system. It's just showing you what is a mechanism. Mechanism is a system where you have rigid bodies and they're doing their own motion. Yeah. Of course, there's also another mechanism here, and we go back to our website here. Yeah, you can see your bike. Yeah, so your bike is going to change rotation, which is a rotation motion, and then of course you can also go translation, which is same as our car, going straight for translation, and then you also have rotating wheel right there. This wheel is rotation. And then going forward is a translation, rotation and translation. Okay. Going on in there. So that's what we're seeing here. And when you carefully look at it, what do you see is look at these. System of gears. See, that is this part to make the motion, to generate motion, and of course we are using our energy transferred to this pedal, and that pedal is going to transfer the energy to the mechanical energy to the gears, and the gears are in a mechanism. Because there are so many gears. Look at that you can change. That's how the relative motions are going on right in there. Okay. And of course we have mechanism, which is another one. So let's go to the next section here. This is just showing you your slot, yeah. So you have your slot contains, you have a pin here, yeah, and then of course you can move the direction of that slot is little thing right there down there, yeah. So you can see this slot is, it has some constraint, by the way. This is called the Geneva wheel, and your Geneva wheel is going to change the continuous, rotation. Where's my pen? Rotation motion, yeah. In your slot, see that how this system is designed to fit into this pin here, yeah. And that is going to generate the motion, yeah. And this is another mechanism, yeah, slot. Let's take a look at some constraint. So when we were studying the slot, we mentioned the constraint. A slot constrain the motion of the pin. This slot is going to constrain the motion of that pin right there. So let's take a look at what constraint is. So your constraint is, it's kind of like friction, very much like the friction against the motion or force. So many of the systems, see now we have, like, look at the lot of gears, they're connecting this giant wheels right there, under the train. So that kind of system, mechanical system that you see in real life, they have a lot of constraint, but because you have to have a constrained motion, otherwise motion is very difficult to be controlled without the constraint. Yeah, so your motion got to be constrained in real life to increase the control, of that mechanism. So many times your complex system, you can model it as simple mechanism, or you can do it like this, very complex, connecting parts, so connecting rigid body system like this. Okay. Um, Depends on the design. But a lot of the people, of course, take it for granted for everything. Some percentage of the people have innovated and created and designed, but they're very difficult to design, by the way. So make sure that you respect, people from the past. They come up with all of that. The most the regular people do is to insult the elder people, like calling them old men, old ladies, and ma'am and sir and things like that. But they have contributed incredible amount of knowledge, to everything that you are using, today. So we have to respect them, Okay, so now we get into different systems. So let's see linear bearings, collars. So this is your linear bearings and your collars, and sleeves that's gonna fit around, or on shelf. They're just showing you, you don't have to worry about if you don't understand it. It's okay. They're just showing you a big mechanism, how many different parts in this exercise, okay, system. So you can be able to, train your muscles to, like do some exercise and enhance your circulation so you stay healthy. So anyways, right now you can be able to see the linear bearings and the collar system. Example is your exercise, mechanism. And then your slot again, your Geneva slot right here, your slot again is going to constrain this pin, and if you want to move in the direction of the slot, you will have to turn this wheel, so it will go into the next, and then the next, and then the next, and then the next. Let me try to find out if we have a Geneva wheel. So this is your from the internet, search. I'm not gonna babysit you by showing you this internet search. You're supposed to be doing it by yourself. So you go to the handout and you listen to the lecture, and you go up on your internet and find visuals to enhance your learning. So this is what the Geneva drive wheel is. So look at this pin, it's gonna go each slot that way, and of course there's some constraint because you're pushing, this pin is sliding into the slot to make the rotation. See like how very cool that is, the design is on. making this creating the motion. Yeah. So anyway, so that's what I want to show you. Alright, then we're gonna go into joints. So joints is pretty easy. Of course, she identified the axis right here, so we know that the axis is pointing upward. And this one is DOF, mean degree of freedom. So there's no degree of freedom, meaning like it is fixed, it can't move. And it's your clamp. And then you have a pin here. You have like a 2 to 3 rotational degree of freedom. This is a 1 rotational degree of freedom with the hinge. That's the pin hinge. Your wheel has like a 1 translational degree of freedom or 1 to 3 rotational degree of freedom. And your ball has a 2 translational degree of freedom and 2 to 3 rotational degree of freedom. Yeah. So these are the rollers. So that's the hinge, so that's a pin, and that's a clamp. So you can be able to understand how the joints, and the different joints, and how it can be able to move, Surface contact, your surface contacts. So when you look at this little cartoon, okay, every time you have a contact with a moving, body, that contact is going to definitely give you friction, meaning constrain that motion, of some point on that rigid body to this profiling the how the road is in this picture, profiling from here to here how the way that the path is designed. So here is just a simple road and your car is going, and there's friction right here, and we call that the constraint point, constraint of that motion. Why? Because they come in contact with the surface. One moment, let me see if I covered this or not. Now this is just for you to listen to how we analyze the mechanism, the complex system. So the very step one, we're going to get familiar with the system, meaning like we will observe the system. So in this example, we have the system here, and we will pay attention to what we have in that system. So we have axis here, we have points there, and we have a points with the velocity given to you, the position here too, and we also have a geometric constraint because of the way that it is structured, or designed. And then of course we'll pay attention to the angular, velocity direction. So everything that has been given in the system that we know, we're going to pay attention to that. So the distance is the point, and how they are connected to each other, every part of it. So that's what we do. First, we analyze and get familiar with the system, and then we're going to pay attention to the velocities. So you're going to start with a fixed point, or known velocity, which is already given to you, and you're going to work outward. Sometimes your relationship for velocity, you can find it from adjacent or connected, system, and then you're going to apply that known information with the geometry in that system. So your geometry, the point of contact surfaces, attachment or joints, they're going to definitely give you frictions or constraint to that motion. So these are everything that we pay attention when we analyze a mechanism. And then of course in step 3, we analyze after velocity, we analyze the acceleration. So acceleration always based on the velocity, so we pay attention to. So anyways, this is for chapter 4. Chapter 4 we cover only 4 sections. You don't have to do the rest of them. So that's a pretty light on you. Alright, I'm gonna go ahead and stop right here.